The recording is on. Class has begun. Hi, Zoomers. Hello, Roomers. Happy Garbage Day. Got the merch. I'm the only person on earth with a Happy Garbage Day t-shirt. Very happy with the ability to wear athleisure to work at this point. That's one nice thing about the pandemic, is that our standards for what is like formal wear have all kind of come down. So quite happy about that. I've got my snow boots, my athleisure wear, we're ready to do it. So I was just saying that I updated grades this morning. I believe that I am caught up on grading homework 3 revisions, and homework 4 finished last night. Not everybody has finished it, but if you have questions about why you missed something, please let me know, and I'm happy to go over that with you individually. The next thing up is homework 5, which is not due until after Thanksgiving. I am having office hours this week, but I hadn't planned on doing so next week since there are no classes. I will be on email, though, if anybody wants to ask for advice or help with respect to estimation or what to do. Let me know. After that, then we just have one more formative assessment and one more assignment. And then we're in the home stretch. So, woohoo! The countdown has begun. Your last homework will be an invariance analysis on CAN data, and it's not due until the end of finals week. My intent is to have your last homework put up over Thanksgiving so that when you come back, you can be working on it as quickly or as not quickly as you wish. So no final exams, hopefully no stress. You can get it done and be on your merry way, whatever your winter break plans happen to be. So let's talk about invariance testing, since that's what your last homework's going to be over. Tell me what you remember about invariance. I got a slide up here to cue your memory. Zoomers, I'll share my screen so you can see what the slide is too. How about that? What's invariance testing about? Why do we do it?
Test how the functions the items are functioning across groups.
Yeah, test how items function across groups. What about the items in particular? Slopes, is that what you said? Slopes is one, otherwise known as what in this class? Loadings, yep, factor loadings. That's one way that an item relates to an outcome that we would be concerned about measurement and variance. What's another?
Thresholds.
Thresholds. Or, if I don't have a threshold, what would I have instead? Intercepts, yes. And if I'm in the world of CFA, what's a third option for invariance that I'd be concerned about? Yeah, error variances and potentially any covariances. So the objective then is to figure out how much model fit gets worse by constraining item measurement model parameters to be equal across groups or across repeated measures of some other kind. And the steps. Should we do vocabulary? A little bit of review on that. What's the first model called? Configural. Yes, and at that stage, what is constrained across groups?
Factor means and variance?
Yes, but they're constrained for identification. With respect to the item measurement parameters, what's constrained across groups at the configural stage?
Nothing.
Nothing, yeah, because it's just broadly construed same factor structure. That's what you want to see. And that should fit, otherwise there's really no point in going forward, because everything you do from that point is going to make it worse. Then after configural comes what? Metric, otherwise known as? Weak, yep. And what are we constraining at that phase? Loadings. And then what do we have to free at the same time?
Factor variance of the alternative in the alternative group.
Yeah, factor variances only in the alternative group. They stay one. They stay nailed down in the reference group so that the entire sample then is linked together through the constraints on the loadings, the scale of the factor variances is given by the constraints in the first group. So they're partially linked together with respect to the loadings and factor variances. And if that's not worse, then yay. What if it's worse? Take our ball and go home? No. That's an expression. It means basically, you know, what it means. What do we do instead of taking our ball and going home? But what if invariance fails at the metric step? How would we address that? Do we quit, or can we do something about it?
We can look at the modification indices and see what parameters can be free.
Yes, so this is where the cheat codes help us. But it's not with respect to adding random error covariances or other things it wants to do still. We would be looking for just the constraints that we had placed on the loadings popping up as a suggestion, because what that would mean is that it wants to be free. So the modification indices can help us identify the source of non-invariance, which loadings are causing the problem. And then we can let those be free and keep the others constrained, going back and forth until we get to not worse as a whole. So partial invariance would be the goal, where most of the loadings are the same, but they don't all have to be. If you have at least one, you're in business. Mathematically, you need one. Conceptually, that is a terrible idea. But one is all you need. That is a song, too. Now it's in my head. What's next? So assuming we have at least partial measurement invariance with respect to the loadings, we keep on going, and the next stage is called scalar, otherwise known as strong. Yes. I'm doing side gestures here. I'm keep everybody awake today. That's my goal. Look at my buffs, as my son would say. He decided that to be buff, like is an expression to be strong, he decided that buff was a synonym for muscle. So you can see him flex in the mirror, and he's like, look at my buffs, man. Like, yes, sweetheart, you're 55 pounds. You're very strong. You know? But yes, my buffs. Strong measurement invariance means we do what? What do we constrain? What do we free? Zoomers are awfully quiet here. Roomers are answering all the questions today. That was a hint. Now I'm the dean again. We constrain the intercepts. Yes, we do. I was telling the other class that the dean came to our faculty meeting yesterday to talk to us, and we were all just like sitting there looking at him like a bunch of sullen teenagers. And he's like, are you guys just tired or what? I'm like, yes, we are. That is correct. But yes, constraining the intercepts. And what do we free at the same time?
Factor mean.
Factor means in which group?
Alternative.
Alternative group. They stay 0 in the reference group because that sets the scale. So at this stage now, the model is on the same scale across groups with respect to factor means and variances. And we would go through the same process. If the invariance likelihood ratio test is significant, that means it's worse. We go back to the modification indices, try and figure out why. Keep iterating back and forth until we hopefully get to at least partial. Then what's the next step? We got loadings, we got intercepts,
Residual variance.
residual variances. Does it have a special name?
Strict.
Strict. Yeah, it doesn't have a special name other than that, but strict. And if that fails, it would mean that the amount of not the factor variance differs across groups. And okay, whatever. We might do residual covariances at that stage as well. Do we have to free anything when we fix the residual variances to be equal? Nope, nothing left at the structural level. So once we've got metric, strong, strict, then we can move to structural tests, right? So we would do factor variances, factor covariances, factor means. And if those don't hold, meaning the groups have different factor variances or different factor covariances or different factor means, is that a problem? Not necessarily. That means at that stage that your groups may have real trait differences that you would care about and want to report. But you need at least partial measurement and variance to be able to say that it's the trait that differs between groups and not the way that the trait is being measured. All right. Questions on any of that thus far? So that is the world of measurement invariance, measurement equivalence, factorial invariance, et cetera, et cetera. The next part of the slide deck is changing into WLSMV, but we're not going to do that just yet, because I wanted to show you a real example. Last time we went through an example with what I am almost certain is fake data, because it was a measure of depression in your textbook in which they had exactly equal numbers of men and women and a 9-point scale, and everything looked perfect, pretty much. And so now I wanted to show you a CFA example that isn't perfect and is real data. So the data that goes with this example is not available in download packet because it is real data from a former student. And as most of the examples that I have for you, this one ended in a happy note because this student did graduate. Okay, the student graduated, they're out in the world with a career, making money, using their PhD, making the world a better place, okay? So I just want to say that, because this was this poor student's dissertation, and you are going to watch this measurement and variance just fall apart. But they still graduated. That's the same. So this is a longitudinal example. So the way that the model is going to be set up is different than the multiple group model. Let me find that picture real quick. It's going to look like this instead. So rather than having separate models for men or women that are in independent groups as the previous example, this is where we're measuring the same trait multiple times within the same person. So the responses are dependent, in other words. And this picture is what it would look like if you had 2 occasions, where I have 4 indicators for each occasion. Each occasion's trait would be in a separate latent factor. Critically, the factors are related to each other. That allows for the dependency of your factor score at time 1 with your factor score at time 2. Dependency means correlation. As well as the fact that if you answered item A twice, those responses may have something else in common because it's to the same item, literally, beyond the factor. And so it's traditional in these models to allow residual covariances for the same item over time, just as a baseline starting point. So this is the type of model that I wanted to show you so that you can see what the code would look like to do these steps differently in an example with dependent data. So this analysis was greatly simplified relative to what it would be in the best case scenario for practical reasons. I only have 151 people. The indicators that I'm using are not actually items. They are some scores. I know. Each of these subscales was composed of multiple items, like 30 items apiece. So if I wanted to do this analysis in the most proper way, I'd end up with like a covariance matrix that's 180 by 180 if I had 6 subscales of 30 items each. And I only have 161 people, and I have 3 occasions. So make that 180 times 3 is what it would actually be in the full data. I do not have enough people to do all of that. So I allowed this student to simplify the analysis by adding shit together to make the subscales, and then treating that subscale as an indicator, where I have 6 indicators of 1 factor, and that factor was measured 3 times. So that's one way in which this was simplified. So the story behind these data is that they were collected from real people in a psychiatric rehabilitation center. So this was a student who was in clinical psychology who was studying this type of rehabilitation process in people with severe mental illness. So these are people who needed help in some kind of restricted facility designed to help keep them safe and to teach them skills to be able to cope with whatever mental illness and other problems that they might have. So occasion one, they're having a lot more fun out there than I am. What are they doing out there? Is the dean out there? Is he having fun with them? Maybe he decides the undergrads are cooler than the faculty. And he's not wrong. But no, I think I shamed them into being quiet. Okay, cool. So occasion one is when they were checked into this rehabilitation center, and occasions 2 and 3 were collected at 6-month intervals. Okay, no problem. Question? Or just waving at me? Okay, all right. Now, the second way in which these data were simplified. The 6 subscales were not self-report. They were completed by people who worked at the hospital. So there is an additional source potentially of dependency that we are ignoring because responses from the same staff member about multiple patients are probably going to be related to each other, particularly with respect to a staff member's perception of the person's social competence, social interest, personal neatness, as well as negatively oriented measures of psychoticism, motor retardation, and irritability. So these are staff member perceptions of the patients, where the first occasion was taken the day they got there. How well do you think a staff member is going to know someone they met 10 minutes ago? Not very well. How well do you think they would know them 6 months later? Better, I would hope. So we are ignoring the dependency of responses due to the same staff member completing the measures, as well as potentially the fact that it might be a different staff member completing the measures later on than before. All of that is being ignored because this poor student wanted to graduate and I wasn't going to stand in his way. So those are the simplifications that were made in order to make this analysis possible within the scope of a dissertation for somebody whose primary area was not quantitative methods. So those are my disclaimers. So I have the words here, what each of these things are measuring. 3 of them are scored such that higher scores mean worse behaviors, like more psychotic, more irritable, and 3 of them are scored so that higher scores imply better behaviors. So the first thing I had to do was flip them so they're going in the same direction. So the latent trait that this person wanted to measure was social functioning broadly. The way that I have named these 6 variables will allow us to understand the code more easily. I have lowercase v for which variable it was, and then uppercase T for which occasion it was. By the way, find and replace within most programs can be made case sensitive. So if you're very strategic in how you use lowercase and uppercase letters, you can find and replace huge chunks of your code with less work. So I'm using lowercase v again for the variables 1, 2, 3, 4, 5, 6, and then T1, T2, and T3 for the combination of 6 measures by 3 occasions. Within M+, which is the code that I have here, there is an option that I haven't shown you yet, I don't think. It's define, and this is how you can make new variables out of the data set that you read in. So I am reflecting them. What is this, additive inverse? Did I get it right? I made an additive inverse. I multiplied it by -1 so that higher scores would be better outcomes. So I've made it so that all 6 indicators are going the same direction where higher scores mean better functioning. I do have Lavon code that goes with this example. It did not come to the same conclusions. So it's not in the handout, but it is in the folder. As before, the trick to constraining parameters within M+ or within Lavon lies in the use of common labels. So for things that you want to have separate across groups, you would give a different label to the parameter for each group. In this case, it's an occasion rather than a group. Things that you want to be the same, you would give the same label to. So all of that works the same way. It's just that because we have 3 occasions that are related to each other, we keep them all in the model at once. So I'm using MLR estimation. This is a CFA model because I have what is a reasonably continuous indicator for each of my 6 variables here. And then the model syntax is what gets changed across each of the models here. Okay, any questions about the story or the intent? So why did I make this student do this for his dissertation? This was not his question. He did not have any research questions about whether or not these measures of social functioning functioned the same way over time. Can you guess why I might have made the student go through this process, even though he didn't really care about that? Hint, hint, what was I talking about an hour and a half ago, for those of you in that class?
You wanted to explore dependency?
Dependency, yeah. We have longitudinal data. When people collect longitudinal data, what do they usually want to know?
If time is significant?
Yeah, if there's change, right? In the context of a hospital, shouldn't they be getting better? Like, hopefully, like that's why they're there. It should be helping them. So this student had questions about whether or not there was improvement in these patients' social functioning and potential questions about differential improvement across people. Who were the clients that were most helped, essentially? Those kinds of questions. Zoomers, welcome to the program. Change over time versus measurement and variance over time. Exactly right. In order to be able to say that it was their social functioning that changed, right, the trait, I need to be able to say that the way the items measured social functioning was the same over time. Right, Chen Chen? In order to measure epistemic orientation, the same way over time, we got to do that before we can see if it grows, right? Yep, I'm making her do the same thing on her dissertation. So I didn't just pick on this one student. I continue to torture students today. I'm an equal opportunity advisor. So yes, this student did not care necessarily about invariance, but he wanted to know about change over time, which presupposes invariance. So that's why we did this. Okay. So here's my configural model. There's a lot of code here because I'm trying to be transparent about what is happening. So I'm listing out all the things that are being estimated, as well as all of the things that are being fixed, so that you will know what is in the model and what's not in the model. So first off here, factor loadings. Let me zoom in here. I named my factors time 1, time 2, and time 3. But they're all measuring social functioning in theory. So I have stars after each of these variable names. What do the stars refer to in the context of this code right here? What am I talking about? What kind of model parameter am I referring to? Feel free to read from the screen. Loadings, yeah. So an M plus a star means it's estimated. If I wanted to do less typing, the only star that I really need to type is after the first ones, because it defaults to fixing the first factor loading to 1 unless you override it with the star. Because of the way that I named these variables, I can't abbreviate. Because it's the first part of the name, the V1, the V2, the V3, that it would need to extrapolate across, and so the T1 is constant, means I have to write everything out. So I've got time 1 for all the ones that end in T1, time 2 for all the ones that end in T2, and time 3 for all the ones that end in time 3. Then in the brackets, I've got item 1 across time, item 2 across time, item 3, 4, 5, 6. And what am I estimating here inside the brackets?
The
Intercepts. Why don't I have thresholds in these models?
Yeah.
Because this is a CFA. And we don't have thresholds in CFA. We have intercepts. Residual variances are next. That's what it is when you refer to a variable just by itself. So those are also freely estimated. Then comes the identification constraints. So at this stage, all 3 factor variances are fixed to 1. All 3 factor means are fixed to 0. So rather than talking about an alternative and reference group, now the words are going to be alternative versus reference occasion. I have to pick one of these occasions to be my reference. At this point, everything is fixed with respect to the factor means and variances for identification so that I can estimate all of the measurement model parameters. So these 3 occasions are not on the same scale. They are not linked together in any way, shape, or form. Each one is basically re-standardized against the others at that occasion by having a factor mean of 0 and a variance of 1. The word with does what? Covariance of some kind. Now, it knows, based on the context of the rest of the model, whether it is a covariance or a residual covariance. What's the difference? I'll give you a hint. These are covariances.
The label?
I called it covariance, but how would I know that that's what it is, as opposed to a residual covariance? It's not a semantic distinction. It's the same difference between a mean and an intercept. Breadth? Is it just brackets? These are either means or intercepts. They're also contextual. These are either variances or residual variances, also contextual. So how do I know which is which for all 3 questions, basically? Means versus intercepts, covariances versus residual covariances, and variances versus residual variances. What are the difference between those things? I'll give you a hint. In this model, my factor, my theta, is it a predictor or an outcome? Thetas are predictors. Factors are predictors, right? Is anything predicting my factor itself? No. So it's just a predictor? That means it gets a mean, a variance, and covariances because it's unpredicted, unconditional. What is being predicted are the subscale scores. So they get intercepts because they become the conditional mean when the factor is 0. They get residual variances instead of variances because it's left over, not the factor variance that's being estimated. And they get residual covariances instead of covariances. So it's a distinction of conditionality. Things that are truly predictors get means, variances, and covariances. Things that are truly outcomes get intercepts, residual variances, and residual covariances, where the latter means left over. So it's a different statement to say that time 1, time 2, and time 3 factor scores are all correlated. Then the code looks exactly the same for the items, for the indicators. But what I'm saying here is it's not that the indicators are related. It's that the part of the indicator that's not the factor is related. The leftover parts are related. Does that make sense? And you wouldn't know from looking at the code. It's all contextual based on the rest of the model. So in lavaan, it calls everything, I think, intercepts and residual variances, but it puts a dot in front of the ones that are unconditional, if I remember correctly. In M+, it actually has separate headings for these. So you'll have to look in different places. So yes, factor variances, and listing all of these with a with in the middle means all 3 of them are estimated at the same time. Likewise, this line right here gives me 3 residual covariances for item 1. So the the covariance between the residuals for item 1 at 1 and 2 gets a relationship, 2 and 3 gets 1, and 1 and 3 gets 1. So there's no constraints on that. All right, no worries. Sick children beckon. That happens. Okay, so this is my configural model. This is going to be as good as it gets with respect to model fit. Nothing is linked together across occasions. The only thing that's constrained is just what I need for identification at each occasion. Okay, with me so far? So let's see what happened. I have 75 free parameters. That means I've estimated 75 things. How many are left over is 114. So that's a bigger model than what we're used to seeing. Why is it so many? I've got 18 variables I'm working with here. 6 indicators by 3 occasions. I've got an 18 by 18 covariance matrix plus 18 means. So the total amount of degrees of freedom that I would have is the number of parameters that I estimated, which is 75, plus the model degrees of freedom for how many are left over. So what's 114 plus 75? The answer is not on the slide, but you can figure it out. Let's see, that would be 189? Does that sound right? Doing math in my head is always dangerous. I know. But sometimes I ask this in homework questions and I'm giving you the tricks. Like, this is how you know. Well, how many are left? That's always your chi-square test. How much you spend? That's always up here. Left plus spent gets you back to total. But it would also be 18 times 18 times plus 1 divided by 2 plus 18. That formula works as well. All right, so first off then, my model, how would you describe the fit of this model? There's my chi-square, there's my RMSEA, there's my CFI, there's my SRMR.
Not really bad.
I'd say it's not great, it's not horrible, but it's not like good enough yet, I would say. And so then here's what happened. He sent me this output. Like, this is not really good enough to start with, so can you try to fix it? Maybe my first suggestion was, well, 3 of my indicators had to be reverse coded, so maybe it should be like 1 dimension for the measures that are positive and 1 that are negative. Nope, that wasn't actually better. We tried a few other things, went through a process of trying to make modifications that made sense, that made the model fit better, and ultimately this was as good as it got. So I gave him permission to go ahead and do the invariance testing. However, starting with a model with mediocre fit, what's going to happen from this point? Is it going to get better? It's going to get worse because I'm taking away parameters. So the only one that could get better really is RMSEA. But yeah, this is not ideal. So I made a picture here of the factor loadings. And even though these are not on the same scale, the ones that look more different from each other, I think, are going to foreshadow what's going to happen. Because if factor variances differing over time were the only reason why the factor loadings differ, these would all be proportional to each other. And some of them are not. Like time 1 looks very different than some of the others here. So this is foreshadowing what's going to happen. So here is my configural solution, where we have the factor loadings per occasion. We have the factor covariances, so they are fairly highly related over time, but not perfectly. I omitted a bunch of the residual covariances among the same item because we're not going to touch those. We're just going to leave them in the model. You might consider getting rid of some of those if you don't need them at the end, but for now we're leaving them in. And over here, note that some of these items have some weird looking values. That's because they were multiplied by -1. So that's why they're negative like that. Doesn't matter so long as everything is internally consistent. All right. So what's my first step here? Metric. So unlike the model and then model something else version that we had last time, here all of the constraints are going to be within the same model. So I have L1 to L6 that has been added to all 3 of these lines. So when you add your constraints, the labels only apply to parameters that are listed in the same physical line of code. You literally cannot hit return. If I did this, it won't work. I know that's ridiculous, but that is the way that it is. So the labels have to go on the same line. So it understands that I mean an abbreviation of L1, L2, L3, all the way up to L6, but it's going to read the labels in order of the estimated parameters on that same physical line of code. So L1 now refers to that loading, and that loading. By giving them the same name, I'm making them the same. That's how the constraint works. And you could call it whatever you want. I'm picking L because it stands for loading. The rest of the code is the same, except for what? What do I have to do if I fix the loadings to be equal?
Factor variance
Yep,
equal, previous estimate.
right there. So the factor variance is still fixed to 1 at occasion 1 because I've made that my reference occasion. That it is free on the other two.
This-
Yeah.
But, well, in the other two factors, the interpretation for the new parameter estimates will be that they have more or less variability with respect to group 1? Or
With
time
respect
1?
to occasion 1, that is right.
Occasion 1, okay.
Mhm.
But time 2 will be compared to time 1 and time 3 with time 1 again, right?
Yes.
Like a dummy codification.
Yes, yes, you
Okay.
can think of it. Yeah, so these numbers only have meaning relative to 1 as my anchor point.
In terms of more or less variability.
Correct.
Okay.
So if the people become more variable at the later of occasions, you would see variances above 1. If they become more closer together, more homogeneous, then the variance should be less than 1.
Good.
Yep. And again, the reason that I did it this way, the hill that I will die on, is otherwise, if say I had fixed all of these loadings to 1 as markers, what am I assuming about it? If I fix a factor loading to be equal to, or excuse me, to be fixed to 1 as a marker item, what am I assuming about it?
That the factor loading is 1?
If I make them all 1 to identify the model, what am I assuming with respect to their invariance?
They don't vary?
They what?
They won't vary across groups?
They can't vary. Yeah. So if I had identified the model by putting these at 1, right, which is the default, mind you, if that's what I had done, then this is a constraint that I can't test. I can't see if 1 is different than 1. It's not. Spoiler alert, it's not going to be. So to make sure that I can test all the loadings, I've identified the model so that one of the factor variances is fixed to 1, the others are estimated. Otherwise, I would not be able to test the first loading. And it turns out that I'm going to need to do that. Survey says, so there's a spreadsheet that goes with this example where I did all the likelihood ratio tests. You can use ANOVA and R to do this. So my -2 log likelihood difference, rescaled, of course, 10 degrees of freedom. So in this case, let's count them up. How many loadings did I have before? I had 18. How many factor variances did I have before? I had 0. How many loadings do I have now?
6.
6. So that should be a savings of 12, except that I had to free my 2 variances. So that's where the 10 comes from. And I have a chi-square test statistic. So the difference in -2 log likelihood, other folks will call that a chi-square because that is what we do with it, is compare it to a chi-square reference distribution. Gives me a p-value of 0.04. What's that mean?
The new model fits significantly worse.
Yeah, worse. That means I got to figure out why. So here are, yep, chi-square is up. Our MSEA is a little bit better than it was before because that one likes parsimony, but the others are all getting worse. Here's my modification indices. There's, of course, way, way more than these. You have to kind of like dig through them to find the ones that are right. But here, by statements, what are those referring to?
Cross-loading?
Cross-loadings or loadings, right? So usually it's a cross-loading because it's suggesting a loading that you don't already have. So I narrowed it down to just the ones that are potentially relevant, like the largest one here that's first. It says, you know what? You should let variable 1, measured at time 1, load on the time 1 factor. And I'm like, I thought I did. No, actually, you didn't let it load enough. The idea of not enough is, you know what, if you let it have its own loading, if you didn't constrain it to the loading at 2 and 3, this is how much your chi-square would improve, and this is the difference that the loading would be. The EPC is the expected parameter change. So when it tells you to add a parameter that you already have, what it's telling you is that to release the constraint on that parameter. So in terms of the omnibus test, the result of constraining all the loadings was a worsening of the chi-square by 19. This is saying that like half of that was due to one of them. Item 1 wants to have its own loading. It wants to be more related at time 1 than the other two. Okay, we can do that. So model 2B then, partial metric invariance. See if you can spot the difference in the code. We'll play Where's Waldo, M+ code style. What did I do to this to make it a partial invariance model?
L1A.
That's it. Right, there it is. A, because why not? Doesn't matter what you type. It could be this one. As long as it's 8 characters or fewer, you can type whatever you want. But A works because I'm already using 1 to keep track of time 1, so I went with letters instead. But point being, this label differs from these two. So the model is now saying the loading for item 1 at time 1 can be whatever it wants. The loading for item 1 at times 2 and 3 is still locked down into being L1. So the more occasions or the more groups you have, the more combinations are possible. What if I had 4 occasions? Then I could have like 6 differences, right? 1 could be the same as 2 or not, 3 or not, 4 or not, 2 could be the same as 3 or not, 2 could be the same as 4 or not, 3 could be the same as 4 or not. A lot of combinations. That's how you can end up with like scalar R. In terms of like testing all the things, that's how. That poor student had like 5 groups or something. So this seems like it should work. This is the only change that I made. Releasing 1 constraint. Survey says, I did 2 different likelihood ratio tests to answer the question. One is, am I heading in the right direction? So I compared the partial metric model to the full metric model. So in this case, what I want to know is, did releasing the first items loading at time 1 help relative to when it was all nailed together? Yes, it did. Then the question, is it enough? So now I compare my partial metric model back to the configural model with degrees of freedom 9, because I had to give 1 up. And yes, it looks like now it's non-significant. I went through and looked at the modification indices, and they were all fine with the remaining loadings, and so we're done with metric. So then here's what happened. Whatever item 1 is more important to the factor, is more related to the factor at time 1 than it is at 2 and 3. I can do armchair quarterback, as the expression is, which refers to people who are sitting watching sports in their living room, pretending like they would make a better decision than all the coaches who are on the field. So I'm going to armchair quarterback this and say the first item was social competence. So whatever that means, it is more important to the measurement of that factor at the first occasion, as rated by the hospital staff, remind you. Okay, cool. You had asked about the factor variances. Let's go find those. Here they are. So the factor variance at time 1, the estimate is 1, the standard error is 0, and the test statistic is 999. Is that a lot? Is 999 a number? Not really. That's what M+ gives you when you fixed something to 1. It has no standard error because there is no estimation error if you fix it. And 1 divided by 0 is 9999. I know that you can't divide by 0. Is there a name for that? Undefined? Okay. So 999 means undefined. Not missing, but just like impossible. Time 2, factor variance is 1.1, so it looks like they're a little bit bigger. The test statistic for that variance is 6.2. Can I conclude that these variances are different from each other based on this? Because it's tempting to. Test statistic is 6.3 with a p-value of 0 to 3 decimal places. Does this tell me that these two numbers are different?
I would say yes.
I would say no.
Why?
Why? Because this is against 0, not 1. Wald tests are always against 0. I know, it's tempting. I'm pointing out all the misconceptions that I see people make that are very tempting to make. If I wanted to test whether 1 and 1.1 are different, how else could I do it?
Linear combinations or changing the reference value for the null hypothesis?
Linear combination is one approach.
Okay.
So I could write a new parameter that is the difference between these two numbers and test it against 0. That would be one option. The other would be to make them both 1 and see if the model fit gets worse. So that's eventually where we're going to end up with our structural constraints, is the latter. But we're not there yet. So it looks like, just eyeballing it, people are slightly more variable at time 2, they're slightly less variable at time 3. There's a lot of missing data, though, as you might imagine. We're assuming anything that's missing is missing at random, meaning it's conditionally missing, or conditionally random after factoring in the information we do have. But yeah, we don't know yet if these variances are different from each other. We know that they're different from 0, but that we expected in the first place. All right. Everything else over here is relatively the same, not of note just yet. Let me go back to the picture I had made. So this picture is of the intercepts from the partial measurement and variance model. Again, we're looking for disproportionality, essentially. So what these are the expected item response for a factor score of 0. If the factor is what's changing, then we should see basically that all of these differences are caused by factor differences. We would release the factor mean to allow those differences to exist, and then they should be the same. So it looks like, for instance, the first item is growing over time in terms of its means, 2 and 3 are, but these ones don't have the same pattern. So again, this is foreshadowing what's going to happen when it looks disproportionate across time. So here's scalar. So note that I am keeping the loading pattern with the labels the same as before. So I'm letting item 1 have its own loading for time 1. Because of that, I'm going single elimination tournament here, where, blow this up so you can see a little more carefully, because parentheses matter. So do you see the semicolon right here? That makes it so that this label does not apply to it. So this I1 label only refers to the part that is within its own semicolon here. This one is treated as separate because of the semicolon. If I forgot the semicolon, they'd all be linked together again.
Do we have to give it a name?
No, it doesn't have a name. So you can name it if you want. Sad. That's its name. And then this one is, these two are named I1. Yep, it doesn't need a name because we're not saying anything about it. So we are not even testing this intercept because of its loading being kicked out here. The intercept could differ because the slope differs. So for that reason, we're letting it alone. So the rest of these then are, despite the spaces, they're in the same bracket without a semicolon. That's why I2 is going to apply to all of these. I3 is going to apply to all of these. So not a lot of typing, but a lot of nuance to the typing. Very easy to screw this up. How do you know if M plus is doing what you asked it to? Look at your results. You'll see if the numbers are the same or not. And if they're not, that means there's something awry in how you asked for it to do the constraints. So by constraining all of the intercepts otherwise to be the same over time, what do I have to free? What structural constraint do I have to free in order to force the intercepts to all be equal? Last time we did loadings and variances. This time we do intercepts and
Vector means.
vector means. So yes, indeed. Right here. That's the rest of it. So time 1's factor mean is still fixed to 0 for identification. The factor means at 2 and 3 are estimated. So what we are saying is that the only reason why these means differed over time is because of mean change in the factor. That mean change in the factor then should trickle down to our item responses. But conditional on a factor score of 0, all of our indicators should have the same expected response. So now everything is linked together across time, both on the mean side and the variance side. These are on the same scale. So at the first occasion, the mean of the factor is 0. It can be whatever it wants to become at occasions 2 and 3. Likewise, at the first occasion, the variance of the factor is 1. The variance of the factor subsequently can be whatever it needs to be. Survey says, chi-square change of 55. Oops. Cruise on over to my modification indices. Note that fit, bad, bad, bad. It says, hey, you should give item 5 at time 1 its own intercept. And your chi-square would get better by 20. Okay, let's try that. And then this is the point where I knew that we would have lost our will to live. And I just decided to highlight it for you. That one. That's the one. So the part in yellow is model 3B. So we do the same trick where we semicolon off the first occasion from the other two, releasing its constraint. Did we head in the right direction? Yes, freeing that one intercept improved the model. Are we there yet in terms of partial invariance? Nope. Okay, go over here. Next, how about item 4 at time 1? All right, let's try that one. We're up to 3C. Same trick by semicoloning off. Is that a verb now? I just made it a verb. I'm semicoloning. Did we make it better? Yes. Is it good enough? Oh, so close. But no, even though some could argue, I would still want to check. And yeah, one item is responsible for the remainder of the misfit, basically. All right, item 2. I'm at 3D. So I semicolon off item 2. Is it better? Yes. Is it good enough yet? Hooray! So partial scalar invariance. Here is these are the residual variances, I think. Is that right? I think so. Here's what we ended up with in terms of the results. So item 1, relative to the other occasions, has a lower expected response at time 1 than it does at the other 2. Item 2 has a lower expected response at time 1 than times 2 and 3. 4 has a higher expected response at time 1, and 5 has a higher expected response. So in describing partial invariance, it's not enough to be like, they differed. The reader wants to know how. So we would say things like, for the loadings, for instance, item 1 is more discriminating at time 1 than it is at the other occasions, right? It's more related, and that's why it's non-invariant. With respect to the intercepts, for whatever reason, the positive items look like they're easier. They would have, yeah, nope, this is intercepts, sorry, wrong class. They're harder, they have lower expected responses at the same level of the trait. So you would want to report the direction of how these differ from each other. Intercepts are lower for items 1 and 2. They are higher for items 4 and 5. All right, how are we doing? So at this point, if we look at the code, this is my record as to what happened at each stage, and I would recommend in your code that you give yourself a record. That way you can reconstruct your process. Like, I freed this at 3A, I freed this one at 3B, this one at 3C, this one at 3D. So time 1 is only being held together to the other occasions by 2 items at this point. So if I want to be able to say that these patients improved their social functioning between when they were admitted at time 1 and 6 months later, I've got 2 out of 6 items to do that with. The other 4 declined for some other reason, or they were different for some other reason, because they didn't match what happened with the rest of the indicators. So then right off the bat, with respect to residual invariance, all of these things automatically get semicoloned out of the tournament here because they failed the scalar stage. So we're still testing equality of the error variances that are left over time. So between 2 and 3 for items 1, 2, 4, and 5, and between occasions 1, 2, and 3 for items 3 and 6. Nothing else changes with respect to the structural model. Of course, it fit worse. Modification indices want us to do item 5 across times 2 and 3. And note that these are the same number. It wants to free item 5 either from time 2 or time 3 because that is the only constraint that's left. So it's these 2. So it's saying you can free one or you can free the other. You would have the same result because occasion 1 is already separate. So I do that. There's the change. So I've dropped the label. I've added a semicolon here for symmetry with the code. Am I headed in the right direction? Yes. Is it still worse than partial? Of course it is. So then we need item 6 residual variance from time 1 is the next one that it says chi-square would improve by 13 if we did that. So now we're at this one here. So I dropped off time 1, and I'm keeping the constraints on 2 and 3. Then finally we're good. So didn't I warn you like a week ago that this was tedious? Didn't I use that word? This is what I mean. So we're up to scalar E. So this process, if you ended up choosing a different constraint to free initially, you might end up in a completely different place by the end, because all of these things are like tied to each other. Here's our final unstandardized solution. So highlighting the ones that are different. Relative to the other items, I would say the variance that's not the factor is less at time 1 for the first item. The variance that is not the factor is more for the second item at the first occasion. The variance that is not the factor is more at the first occasion for item 4. They're all different for item 5, and there's more variance that's not the factor for item 6 at the first occasion as well. So we're at partial invariance, but being able to talk about factor level change is going to be a bit tricky, tenuous at best. But from here, it speeds up real quick. So having passed measurement invariance at least to a reasonable degree to keep going, the next step is factor variances. So this is the point where we would reconstrain the factor variances all back to 1 to see if it makes the model worse. So this is a structural constraint. Survey says, nope, it's fine. So how about the covariances over time? This is what they were. Does it look like I can make all 3 of those the same number and have it be okay? Kind of looks like it. Survey says, how do I do that? A new label. So this line of code right here refers to 3 distinct covariances. I've used one word for all 3. That means make them the same. Likelihood ratio test, non-significant. Yep, they can all be the same. Here's my factor means. So do I need to do anything with respect to testing whether time 2 differs from time 1 or time 3 differs from time 1? I do not, because these wald tests are already against 0, just like every wald test ever is, and 0 is what the time 1 score is. So this output right here tells me that 0.284 is significantly higher than 0, and this output tells me that 0.52 is significantly higher than 0 as well. What I don't know is whether those 2 numbers are the same. I don't know whether the time 2 and time 3 means differ from each other. I could do that as a linear combination, or I can do that as a constraint. Say that again?
Can you explain like why again?
Why?
Yeah, like why you can't say time 2 and time 3.
So each of these tests right here, estimate divided by standard error is the test statistic 3.6, for instance, and here's the p-value that goes with it. These are against 0. For identification, the time 1 mean is 0. So each of these individual wald tests is telling me that that factor mean is significantly greater than 0. But they are not in reference to each other. So to find that out, what I have to do is force these 2 factor means to be the same and see if the fit gets worse. I could also write a linear combination for their difference and to put that in the model as well. That's another choice. So I did the constraint version of it. So note that it's still fixed to 0 at time 1 for identification. And then I just put the means for time 2 and time 3 into the same constraint, which I called F mean. And it fit worse. That's the only constraint I placed, so I know that that was the problem. And so the common mean made the model fit worse. I don't want to keep it. So then in pictures, here's where we ended up. So item 1 on time 1 is the only loading that wants to be different. Here are the intercepts, where only items 6 and 3 are invariant. So the other ones you can tell which ones are higher or lower. Likewise, for the residual variances, only item 3 held together over time. The others are all different from each other. So trying to describe your non-invariance in addition to just saying it, I think is helpful for your reader to try and interpret what it might mean. So 309, we've almost made it through this entire handout. I will point out that it's a very long results section. Here are all the words that go with all the nested model comparisons. I have a table of fit, and all of the likelihood ratio tests are inside the text. You could also make a table of likelihood ratio tests so that the text simplifies. But in a throwback for those of you who are in both classes this semester, the structural invariance model that we landed on has the same factor variance over time. It has the same factor covariances over time, and only the factor means differed. So the factor means differing, let me go back to what they were when at the last good model. This right here, the factor means differing. That means that people got better on average. Relative to a factor score of 0, they were significantly higher on social functioning at time 2 and time 3 by 0.28 standard deviations and 0.5 standard deviations. That's how I would interpret that. However, the factor variances could be constrained equal over time without hurting the model fit, and so could the covariances. Those of you who are in currently or were in longitudinal, what do we call it if over time you have the same variance and the same covariance in an outcome?
Compound symmetry.
Compound symmetry. What does compound symmetry imply about the presence of between-person differences?
Constant.
Constant. Due to a random intercept only is another way to say that. So what does the end result of this analysis foreshadow about this poor student's dissertation trying to predict individual differences in improvement over time? How well is that going to go? This factor structure is consistent with only a random intercept. So is he going to find prediction of individual differences and change, do you think?
No.
He is not. There aren't any. Game over. He can try. It's not going to go well, and it didn't. This structural invariance is actually bad. Because what he wanted was to examine individual differences and change in the factor. If the factor variance stays the same over time, people are not changing differently. The factor variance has to change if people are on different trajectories. It has to. So this is an example where you don't want invariance. Invariance means that you don't have any individual change to investigate. So no, it was a bummer. But do you remember the disclaimer I gave you at the beginning? This student still graduated. You know what he did with his null findings? He wrote it up, he turned it in, and he graduated. And that's what you should all do too. No matter what happens, you write it up, you turn it in, and you graduate. There are only 2 kinds of dissertations. Do you know about these 2 kinds?
Yeah.
Done and not done. That's it. Nothing else matters. So he got to graduate, and he's off in the world doing good things, even though he had no individual differences in change. All right. So yeah, IFA is going to wait till Thursday, but we're going to do the same thing with item factor models in the same order, just with a little bit different procedure because we're having to use WLSMB instead of MLR. And yes, Kaylin, you are right. We want the done kind. The done kind is the objective here. That's the only kind that matters. All right. Any questions before we call it a day? It's not a good idea. It's not a good idea. So the reason that I allowed this person to do it was pragmatic, because it would have been too many items over too many occasions and not enough people. But this was also a set of scales that are used clinically on a regular basis, and those people would not have questioned whether or not the item should be put together into a scale. Like, that's just how they did things. So rather than fight that uphill battle, I let him do it. Ideally, what I would have wanted to see is an evidence that each set of items held together to form a coherent subscale. And then maybe if I had to put those factor scores into the analysis rather than sum scores, because then at least I could have tested the assumption of unidimensionality of the items for a single subscale and broken it apart into multiple subscales if I needed to. But I allowed the simplification in this case because I am pragmatic and the student needed to graduate. But yeah, the more better way would have been to do it at an item level. Yeah. All right. Anything else for today? All right, then I have office hours tomorrow. Let me know if you need anything, if M+ is throwing up at you or anything else I can help with. Otherwise, thanks for being here. See you Thursday. Bye, Zoomers.